Well, welcome everyone. I'm delighted today to introduce one of my MIT colleagues. I guess I should say one of my much younger MIT colleagues, Ju Lee, who is going to speak with us today about AI and the future of scientific research. We've had many discussions about AI in with this group, and I think we all agree that it can be supremely useful or supremely abusive. It's all about how people choose to use it. And I think we can see demonstrations of the fact that in science and engineering and medical research, it can be used to great advantage. Uh, and with societally beneficial consequences, and I think we can all be very happy about that. But we still have to consider how this will go forward, and what will be the future in terms of using AI and research and medicine and engineering and science, and that's what Ju is going to talk about today. So, Ju, welcome to the Wilson Forum. We're glad to have you with us today, and I'll turn the program over to you.
Thank you. It's great to be here. Really appreciate the warm welcome. Can you see the screen?
I can see that you've started screen sharing, but I don't yet see an image. There you go. Yep.
Okay,
Awesome.
all right.
Good.
So, just lay the background by a plot of the world population for the last 12,000 years. Actually, Homo sapiens have 300,000 year history, but we were only 4 million uh, 12,000 years ago, but it went to 190 million at time of Jesus. And then when I was born, about 50 years ago, 4 billion. And then when my first kid was born, 6 billion. And of course, we are now at 8 billion. Now, uh, this growth is very sharp, but know that there is a drop in the great drop in the East Asian birth rate. And so it may actually come down as quickly as it went up. Uh, but the time scale are, in tens of years. But this is also the time scale where we're going to have a climate crisis, and we're also going to have the AI explosion. So it's interesting. I don't have the number, but you can think about the number of silicon-based AI agents, some of them embodied agents, and how it will look on this chart. Just to remind that we have released this much of CO2 from 1850 to 2020, so 170 years. Uh, but then we're going to release this much CO2 in, well, 24 years, 2050. And it looks like if we go the business as usual way, then the temperature will rise 4.4 Celsius by 2100 end of century. So this is the temperature rise. And then I think probably even more damaging is what happens to the ocean. The pH right now is 8.1. It may go to 7.8 or 7.7. And that's actually a doubling of the proton concentration in the ocean, even 150% bigger concentration. Uh, so this is a big deal. And I just want to say a bit of how I felt personally on the Pi Day 3 years ago. Uh, for about 2 weeks, I felt really unease because I tested GPT-4 to make some Chinese poems, and it can do it pretty well. And I felt actually, I realized it was like one of these, 90s, 80s movies of alien invasion if you just change the L by the I. Because it is sucking information everywhere and it's sort of processing information. But these AI beings are quite different from humans. Uh, they don't really care about agriculture like we do. They don't really care about Kelvin increase. They are made out of metals and semiconductors. They don't care about these sort of things. They care about they very much care about mining critical minerals because you need them to make their hardware. They care about energy. They care about money still. Uh, so one question is if you think long term, what's going to limit it? So one theory is electricity may be the limiting factor. So this is a projection of uh, all the ICT, all the telecommunication, the data farm, your cell phones, your computer and data farms. It's projected to take up a significant chunk of the primary electricity production soon. In fact, last year, OpenAI declared they want to have 250 gigawatt of compute by 2033. And just to calibrate this, the US has 5 times of that. So this is clearly impossible, but just shows you that indeed this may compete with humans, with mom and pop in electricity. So is it possible that silicon-based, whatever you call it, can be limited by electricity? And I'm going to give you an answer based on material science, and this is a work done with my colleagues, Bill Gildes and Jesus de Alamo. The idea is this: we work by shuttling ions in our protein channels, in our neurons. And how do they work if you have this action potential about 100 millivolt? And you really cannot have it more than that because the electrochemical stability window of water is 1.2 volt. So higher than that, you're going to have decomposition of your tissues. And so you apply this action voltage across, something like a few nanometers of your protein membrane channels, and you can shuttle these ions with a fundamental time scale of a millisecond. And this is the fundamental time scale of all carbohydrate-based animals. It limits the speed of neural reflex, it limits the speed of thought in us. But what we have done is we have shuttled protons across a phosphosilicate glass. So this is actually a proton electrolyte. It's insulating to electron, but is conductive to protons. And we apply the 10 volt from palladium hydride. We are able to control the flow of protonation of this tungsten trioxide. And the goal is to change the resistance of this tungsten trioxide, so to achieve so-called in-memory computing, which is more energy efficient. And just to, as a background, when Deep Blue from IBM beat Kasparov, Kasparov's brain is about 20 watt, but the Deep Blue, I think, is like 10 kilowatt. So indeed, the current GPU or the current memory CPU, GPU computing is very energy inefficient. So we now have these so-called neuromorphic architectures which try to do this non-von Neumann computing. And what we showed was that you can actually have more energy efficient than a neuron. This actually is smaller than a neuron. Neuron is a few microns. We are able to actually make it, in terms of thickness, about the same as the membrane protein, but in size, it's actually quite a bit smaller. And it is 5 orders of magnitude faster than water-based biology. Same physical principle, but just brute force, and you can give it faster, 10 nanosecond time scale. And so actually the first author Murat, he started a company called EVA. It's on neuromorphic computing, and the mantra is a very good one: outcompute, outcompete. And he meant, this towards NVIDIA, right? So this is your GPU is going to outcompute them. In fact, this can do solve linear system equations very efficiently. But I also think it's a bit threatening to all carbon-based life forms. And exactly like what Ron said, I also think that uh, there can be a lot of good. Uh, we can have abundant material and products. I believe we can solve the global warming problem. Uh, I'm going to show you how I think that. I just want to say that there's a lot of friction in materials and chemicals research. Uh, Historically, there was never a material invention that took, less than 20 years uh, to get into a heavy industry. Uh, so I organized a symposium called MIT Applied Energy A plus B. A stands for what we do in 20 years before 2045 or 2050. These will be light water nuclear reactors, uh, photovoltaic wind, batteries, uh, recycling, AI, because these are the things which are already here today with us at gigawatt scale, and so we have a chance to scale them up to terawatt scale. Uh, I think fusion and artificial chemical fuels, those I call type B or baby technologies, we still have to nurture them, uh, but we don't expect them, to help us reach net zero, the Paris goal by 2050. Uh, so my point is that I think AI can lubricate this process. Maybe we can be faster from the lab to the economy in less than 20 years if we use AI wisely. But unwisely, as we have seen already in the drone wars in Ukraine, this really can be very bad, especially I think with our current politics. It's very fragmented domestically and internationally. The speed of change is extraordinary. And I think uh, it's not looking very good at this point. All right. So let me start on the positive side. Why do I say there could be abundant material and product? In fact, Elon Musk said maybe the GDP would have a growth of year by year, maybe 20%, in a few years. Uh, well, okay, we have this kind of interactions, and we can, by Newtonian mechanics, describe the trajectories and materials made out of atoms. And if we know the interaction between atoms, uh, this is interatomic potential, then we can predict material behavior. In fact, there is already a very good universal interatomic potential for every element on the periodic table in the form of density functional theory or in quantum chemistry. Problem though is it's slow, and there is also occasionally accuracy problems. So imagine a method which is uh, much faster than density functional theory and more accurate and actually more widely applicable, then this could really do a lot of good. So we have developed deep neural network learning of so-called couple cluster simulations. So this is uh, a factor of 10 more accurate than density functional theory, which have error bar of more than 1K cal per mole. 1K cal per mole is called chemical accuracy. It is the typical error bar of your thermochemical enthalpy measurement. CCSD, on the other hand, has 0.1 kcal per mole error bar. And we have shown that we can use this deep neural network to give you CCSD level of accuracy for much less cost than DFT. So we can reach 0.1 kcal per mole and its order n method. And we can also predict non-ground state properties. So things like homolumo gap, band gap, electric polarizability, optical response, and so forth. So it's also more broadly applicable than the DFT. One of the visiting scientists in my group, he was at MIT for a year. He was a professor from University of Tokyo. We did a work developing this universal potential for the first 18 elements from hydrogen to argon. After he went back to Japan, he generalized it. So now it's a commercial software called Matlantis. When it's this way, it's called a tensor embedded atom network. And using this kind of tools, we can now do precision drug design, materials R&D, critical mining, and refining. And this commercial software is by this leading AI company in Japan called Preferred Networks. Now it covers 96 elements from hydrogen all the way to the actinides to generate this universal potential. So you can throw arbitrary elements and you get way better than this chemical accuracy. It took 2,000 GPU years of training. So basically, imagine from the time of Jesus, you have one GPU workstation and runs up to now, generated 40, now it's more than 50 million configurations. You used active learning algorithm. Basically, whenever this new network is not matching the DFT calculation, you just do more of the DFT calculation and do retraining. And so I think this is a big advance from the computational side. But just having good potential is not enough. We also need to overcome for corrosion problems, for thermomechanical problems, we need to overcome this long timescale challenge because the atoms, their natural vibrational timescale is picosecond. And if you do so-called atomistic molecular dynamics, you get tens of nanoseconds. It will not cover chemical corrosion. It will not cover aging over decadal, or even in the case of nuclear waste, a million-year timescales. So we have used so-called reinforcement learning to build a method which allow us to do these kind of time, temperature, long time transformation predictions. So what I show you is a ternary alloy, and it has so-called chemical short-range order. Basically, if you are a nickel atom, your neighbors may not be equally 33% nickel and cobalt. You may favor, more chromium. So that changes as you anneal it. So, and that's going to change the electrical resistivity. So this is a plot of the annealing kinetics of the electrical resistivity versus time and temperature. And now we're able to do parameter-free. A key word here is there's no fitting parameter of the experimental. So these three are experimental measured timescales, and these triangles are parameter-free predictions from the this kind of learning of the transition kinetics by solving so-called mean first passage time equation iteratively. So we come up with a neural network that characterize the time it takes to approach equilibrium, kind of like your GPS, right? Tells you, oh, if you make a wrong turn, now you take 35 minutes to go to a destination. So there's this like time map, and we solve that problem. So switching on to experiments. So this is a robot that my student built 7 years ago. It mixes several solutes and solvents, and then it measures the ionic conductivity. So this is measurement of the ionic conductivity, and then computer vision readout, and then it actually rings the thing, and then now here is a choice. What is the next experiment you're going to do? Let's say the goal is to optimize the ionic conductivity, but reducing the evaporation of this liquid solution. So this is a toy problem. It's actually first used in mining for gold in South Africa. So say you have some chemical formulation or some material processing regime parameters, and vertical is some kind of performance. Uh, and assume you have no experimental error, and that's a big if. But let's say you have already done 3 experiments. Uh, by doing this Gaussian regression, process regression, you can get this blue curve. So this blue curve actually is the expected mean of those new conditions where you have not yet done the experiment. But then it also gives you this arrow bar. So this arrow bar is the uncertainty from this Gaussian process regression using some kernels, assuming there's no prior knowledge. Now, if you are a scientist, you would actually be tempted to do exploration where you would say, okay, if I do a new experiment here where the uncertainty is very big, then I can reduce the uncertainty. I can zap this uncertainty. And in the information theoretic sense, that is exploration, right? It's like Christopher Columbus, people warned him, if you keep sailing that way, you're going to fall into an abyss. But he want to see what's on the other side, right? So he would do an exploration here. And so that is scientist thinking. But engineers would actually tempted to do so-called exploitation because there are already 3 results and you have a boss and a deadline and you just want to jack this performance up. So if this is the best result, maybe you're just going to explore or exploit nearby regions. And so the algorithm just like Netflix recommends you the next movie to watch, or the Amazon recommend the next merchandise to buy, this recommends the next experiment to do. And it's a balance of uncertainty reduction with some goal of improving the performance. And so in this case, actually, the algorithm recommends let's do exploration. And in fact, it not only zapped uncertainty, but also we are lucky, is a toy problem, we enhance the performance as well. So this is now used to make, let's say, a multi-component battery electrolyte. I have a startup company that called Elementium Materials that make a battery electrolyte, and this is all done in the glove box. And this is fast forward. But generally, we have large language model that studies the literature. We also understands the molecules. I'm going to show you that we can combine this to recommend liquid formulations. And here's another example. So we have a whole bunch of chloride or nitrate salts. So this is vanadium, iron, copper, nickel, cobalt, chromium, manganese. And then we first mix them in a well. We homogenize this multimetallic liquid, and then we drop it on a carbon paper, and each drop is customized. They're not the same composition. And then we use this so-called carbothermal shock, where instantaneously the temperature can actually go up to 3000 Kelvin within tens of milliseconds. And that caused the metal salt to decompose. So the chlorine and the nitrate decompose. You're left with a molten metal, and they would melt on, they would actually form alloy particles on the carbon strip. And then we cut up the carbon strip, and then we load these up into a 3 electrode setup. We scan the voltage, get the current, and then we can rinse it, and then repeat the next one. So overnight, we can have 20, 50 results, and next day, it can make a new batch of catalyst. So this is called a self-driving lab, and we wrote a review on the issues with this kind of lab automation. It turns out to be a very non-trivial philosophical thing. For one thing, it turns out that we found quite a bit of reproducibility issues. Uh, that's not solved initially just with robots. You would think, with robots, it's more reproducible than humans, but it turns out that that's not true, number one. And number two is that sometimes it's not the experiment that's wrong, it's the hypothesis that's wrong. I just give the example of discovery of antibiotics. It was a failed experiment if your goal is to grow bacterial culture, right? Your goal is to grow uniform culture. You find there's a ring where there's no bacteria. So you, based on the original hypothesis, you would chuck this out, it's a failed growth experiment. But if you know, think that really there's no wrong experiment, these are atoms and they react with each other, you would say, okay, what happened to my experiment? Maybe there's some pollution of this culture, but if you turn your hypothesis around, that actually is a discovery of antibiotics. So traditionally, humans are very good with fluid intelligence. And this is not the same as this Bayesian optimization thing. That actually we build a narrative as we do the experiment. And sometimes even in the second or the third experiment, you see the graduate student getting very emotional, cursing. That's like because he's rebuilding his, narrative. And so that's like one thing we noticed that uh, reproducibility sometimes can be actually a good thing. But then there are also issues of interoperability. So right now, a lot of self-driving labs are too small and too rigid. So you need a system that can sort of dynamically recompile the workflow and can also link up with other self-driving labs. So I just show you some of the things we have gone through. This is trying to make these 8, 9 element catalyst. And it took us actually a year to actually achieve this result. So these are different recipes in the computer, but these are actual samples. These are made in June, and these were made in July, a month apart. And with the same sample, the blue is the first test, orange the second test. And green is the third test. So you see the overpotential is dropping. So this is so-called activation process. Your sample is getting better as you use it. So what we see that a month later, we pretty much get the same performance, but almost similar trend as well. So this is actually a good reproducibility test. But before that, we have lots of troubles. So this, if you see, the droplets that we drop on the paper are not the same size, and we only notice after some time. And they also wet the paper not with the same speed, like this goes in right away. Some of these goes much slower, right? This is a bug in hardware. And the reason is actually after the shocking, the paper actually has some curvature. And so some regions have a good contact, some region not even drop down the liquid, sometimes even can't drop down on it. And so another problem is, after a while, we found, we cannot have reproducible result. Turns out that we have a chlorate electrolyte, and that corrode my copper contact. And so we spent a few $100s, bought a pure gold, and then they solved that problem. And this is a problem that bothered us for many months. I'm very ashamed to say, and I can give you a reason. So this is what's supposed to happen. We have two liquids, and we use the pipette to do this rapid aspiration and homogenize it. We're just trying to mix the liquid. This is what we think happened, but this is what actually happened. We had too small a pipette and not vigorous enough mixing. And so we have this cocktail effect. And as you can imagine, we then take this as our homogenized liquid, and we have all kinds of data. The problem, though, is that this is at the waste level. We are always looking down. So we have two graduate students looking down on this. It looks homogeneous, right? And, so automation does not automatically guarantee reproducibility. So we have these kind of like serial killers uh, in this AI system, and we tabulate them. And anyway, so let me check if I can share the 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 sound, because sometimes if I don't click, I will not hear this. I think now it's good, and I will share it again. Uh, you can hear and see, right?
Yeah.
Okay. So
Hi, Chris. Let's get started.
Sure, Chu. Before we begin, could you please let me know the name of the project we will be working on today?
Well, could you remind me the project's under my name now?
So what we have developed is like an operating system that converts natural language to Python, uh, because some experimentalists are not good with coding. And so this is kind of the AutoGPT function with coding, but now we wrote these Python codes over 2 years. It only took us like 2 weeks to glue a word, I mean, this verbal interface with the experiment.
1. Project name, acidico-ER iridium, ruthenium nickel. Description, oxygen evolution reaction in acidic condition with iridium, ruthenium nickel catalyst. 2. Project name, acidic MOR, platinum ruthenium scandium. Description, methanol oxidation reaction in acidic condition. Please let me know which project you would like to work on today.
I want to do MOR today.
So you see that initially AI thought it just want to do more today, but then later it corrected it.
Working on the acidic MOR platinum ruthenium scandium project.
So this shows the large model is aware of the context.
First task is
And there's no hard coding in this, and that's the magic. It really shocked us how easy it is to, we spent 2 years writing this basement code, but then it's really easy to do this.
batch of experiments. Would you like to manually select the recipe or have it automatically selected by the active learner? Please let me know once you have
Well, the first part you have seen, but it's just
Great. Thank you for confirming, Chu. Next, I need to know if you would like to be notified by email when the experiment is started and finished. Please let me know your preference.
Yeah, I'll be heading to lunch soon, so yes, please let me know.
Understood, Chu. I will make sure to notify you by email when the experiment is started and finished. Now please articulate the command start sample preparation to initiate the OpenTron's liquid handling robot for the next batch of samples.
Start sample prep.
yeah. So the left are all the Python codes that drive the hardware.
Liquid handling robot has started the sample preparation process. You will receive an email notification once the experiment is finished.
I'll let you know when I finish.
Well, understood.
I've already loaded carbon substrate onto the laser cutter. Can I start it?
Sure. I have started the laser cutter. It will begin cutting the carbon substrate. Let me know if there is anything else I can assist you with.
Yeah, I think we can start the pump now.
The pump has been turned on. It is now running. Let me know if there is anything else I can assist you with.
Also, can you turn on the gas?
The gas has been turned on. It is now flowing. Let me know if there is anything else I can assist you with.
So we also connect with some ab initio calculation database. So we have a ternary system. So initially it says stable phases, but then it turns into phases, and then it connects to the Berkeley database, which have the computed intermetallic compounds.
Stable phases are 1. Scandium-2 platinum. 2.
Anyway, so this is like an operating system, and we actually won the NeurIPS award for the best student poster. I just want to show that AI can be used to make some hypotheses and use it for automatic debugging. So initially, I mean, later we made a stainless steel sample holder because we found that the liquid can still cross-contaminate. Even sometimes, you don't see the like the mark of the liquid, it actually probably creeping along the carbon fiber. Initially, though, we just use a piece of wood. But this wood, of course, you see got damaged. So this is testing, whether AI just with one image can tell us something, what might be wrong with making this sample holder. And this have no training of the AI at all. It's a zero-shot learning.
Cutting machine to cut the plywood for making a sample stage. I set the laser cutting parameters consistent across the sample stage, but apparently I got a failure piece. Could you analyze this phenomenon? Hey Meta, take a picture.
The image analysis reveals two main anomalies: non-uniform cut depths and some charring. These could be due to inconsistent material density or variations in the plywood's thickness, resulting in uneven cuts despite uniform settings. Another possibility is that the laser's focal point or distance may have shifted during the cutting process, causing inconsistency in cutting depths and potential charring.
So it turned out to be not too bad. We actually use this later. So it's not genius, but it's not too bad. And then we also have this script-driven SEM, so we can have complete AI controlling this equipment. I think this is the first time large language model have controlled a microscope and resolve down to 2 nanometer resolution. We happen to have a piece of steel nearby, so this is the experiment.
Hi Grass, please take a picture of the boundary between austenite and martensite with field width of 80 microns.
So austenite and martensite are two kind of structures in steel, but initially just understood as merchandise. But by the time it came to here, it corrected to martensite. And then this SEM just have two functions, move in X and Y, and then zoom in and zoom out. There is a third function, which is called segment anything, which is just outline some features. So we just have these 3 subroutines, and AI just learn to control these, issue these 3 commands. There's no hard coding by human at all. We did not tell it what's martensite, what's austenite. This is like the first time. So as it make an image, it start to make some comments. Current field of is this, and they start to see something. It's a little bit like a kid. Actually, it asks about perlite in one of our runs, even though in the command, we didn't say anything about perlite. It says, there's a perlite. It's like a toddler. So now it says it has found this martensite, and then it's going to expand it, zoom in, and then declare success.
Ju, just a question. Just a question. The machine was actually driving the.
Yes.
So
So of course, the large models have already read a lot of literatures that have seen micrographs.
But
But
did
this
it
is a
did it identify Martin sites?
yes,
It did.
it did. So with zero shot, like we did not tell it what's a martensite. We didn't
Yeah.
tell it anything. That's the only thing we told it.
Yeah.
I mean, the reason is it has seen, literature, here's a micrograph, and then in the figure caption, it says it's a martensite, but we didn't tell it how to control the SEM.
Yeah.
We give it, these three functions with some documentation. It reads documentation, it understands that you have an imaging device, and it's able to find
Martensite with a field width of 80 microns. The process involved adjusting the initial field width, locating the region of interest, and fine-tuning the settings to achieve the desired image.
So, what we think in the future will happen is you can have AI that make hypotheses. In fact, right after my depression, we wrote a paper. We checked that for quantum materials, for batteries, for metallurgy, it actually is actually able to have some creativity. And one reason for the creativity is it has read way more books and papers than any of humans, right? A very good human in our lifetime maybe read a few thousand books. It has read millions of books and tens of millions of papers today. It knows about religion, it knows about biology, it knows about sociology, it knows about materials. And we know, for example, the same word, for example, evolution, in biology and in materials. It means maybe somewhat similar things, but also a little bit different. So one thing we think, the reason it can be creative, it just perturb the meaning of words. It's like you're just having these mutations of the memes. Just by changing the meaning of words, playing with words, you can actually, generate new ideas. But of course, a lot of crazy ideas. The key is how do we design the cheapest and fastest experiment to separate the crazy from the true creative. And there's always like a fine line there. And then, and also how do we have reproducible experiments? And you can also have adversarial peer reviews. You can have AI write newsletters, but you can also have peer reviews, which try to pick holes in the hypothesis and to drive this iteration. So I think the key is in building narratives. So generally, I think there are three pillars to science. There used to be only two pillars, but now there are three. There is the simulation slash codes. There is also experiment. So one work with bits, the other work with atoms, and both generate data. And then you also have the theory slash narrative engine. And so you need all three parts to have this AI-driven science. So in the last sort of 10 minutes also, I'm just going to focus on some recent work we have done. Is that the vanilla Bayesian optimization assume you have a robot that goes in and knows nothing. That's only taught by new experiments. But we actually have this so-called word model. And let's say I want to make some multiple salt liquid electrolyte. And I can query this word model, which has read many papers. What do you think about functional roles, right? Functional roles, of course, is a multidimensional thing of this lithium FSI salt in, let's say, NMC cathode and graphite anode at 50 Celsius, if I want to cycle it for 2000 cycles. What do you think about this molecule in this context? And it's going to give me an embedding vector that is, let's say, 100-dimensional. And so I'm going to ask about all my molecules. These are actually the molecules I have in my lab at the beginning in our glove boxes. So for each of these solvent or salt molecule, you give me a 100-dimensional vector, and I'm going to run a principal component analysis. I'm going to get the two most important metrics or vectors that describe these 12 molecules. And so these embedding vectors can come from a computational database of the molecular size, of their electronegativity, the frontier orbital. It can also be coming from this kind of literature encoding of these properties. There is actually 1 million molecules in the PubChem database. So I do some experiments. I find a region where there's actually good performance in my initial mixture of these 12 molecules. I identify a promised land, but then I see which of these database molecules are close to the promised land. I can get a factor of 1,000 reduction, I can get 1,000. I can't buy 1,000 molecules. So I then do some additional calculations. I calculate their oxidation stability, their donor number, which is the solubility, and then whether they're available or toxic, in Sigma Aldrich. So we then bought 10 of these from 1,000. So actually literally bought 10 additional molecules. And then what we do is, as we do new experiments, the AI talks with the human researcher. So the human researcher, that new corpus is incorporated into the word model. There'll be new micrographs. There'll be more cyclic-voltammogram curves. So we have this multimodal feedback that update the word model and it update the hypothesis. So my point is, if you look at, let's say, high temperature superconductor, how Bednorz and Mueller find YBCO. He was a postdoc. He was at IBM. We in Rush-Lincoln felt, the keyword is felt, that polarons are important. You should have a big electron density state at the Fermi level. You should have a Young-Taylor distortion. You should have maybe a wide polaron. So we felt that nickel, iron, and copper could be good. And then we really started to do this in 83, but we found in 85. So the point is that we now have a method to embed human knowledge into the AI. And there's a company led by Dr. Pablo Ducru from also nuclear engineering department, a company called Origins AI that tried to do this kind of AI for science learning. And the example we ran was we found an 8-element catalyst it's a high entropy catalyst for fuel cells or electrolyzer applications. In the last few minutes, I just want to talk about some work we've done in power to gas or power to liquid. So these are taking excess electricity and make them into chemical fuels. Although I think the US now is in dire shortage of electricity, and going from chemical to electricity is maybe the right way. From electricity to chemicals, it's probably not the right way for the US right now. It's maybe the way for China. But what we have found was if you have intermittent electricity, we can turn that into these metal formate salts. We produce so much of them that they can drop out of the liquid, and these can be stored. There's no corrosion issue with this for many, many decades. And then we can use these kind of fuels to generate electricity. And one big problem in a lot of fuel cells, for example, Dirac formate fuel cells, is a poisoning problem, which is the catalyst gets covered by some intermediate molecules like carbon monoxide, and that smothers the surface and make the power density really, really low compared to competing fuel cells. Now, if you change the voltage direction, you can kind of burn away those carbon monoxide, and then you can have the power goes back up. So by having a non-constant electrochemical voltage, you can get overall better, more energy out of your fuel cell. So we developed something called alpha fuel cell, which is a kind of a reinforcement learning that have an actor and have a critic, that for any new catalyst or device you've made, it's a customized essentially a nonlinear controller that give you this time-dependent control that optimize the performance. So we are trying to do certain scale up in the AI for materials, and this is an example where we take used battery packs. People would disassemble the battery pack, turn them into aluminum current collector, copper current collector, graphite separator, but then you would end up with this cathode, so-called black mass. Now, this is like a mineral. This is a very dirty mix of lithium iron phosphate, some iron phosphate, some iron oxide, some PVDF binder, some electrolyte residue, carbon black conductive agents, copper particles, aluminum particles. And so we can do this automated mineralogy, script-driven SEM and XRD to firstly know what we have in the incoming mineral and then come up with processing schemes. We have used a committee of AI. We found that GPT sometimes is very assertive, disagreeable, whereas Gemini is too agreeable. So we actually have a sort of a committee that we say, you should play nice with each other, you should listen to each other, and then together you control the SEM, and that turned out to improve the performance. And I have a company that in 2025 went into production, and now it has sold 1,000 tons of these recycled lithium iron phosphate. So just to sort of to end, I think there is really something about doing good with AI. But I just like to end with a kind of a new article I wrote. These are the last 3 pages. Is that if you compute what it takes to do interplanetary travel, you will see that it's nearly impossible, unlike the movies, for human in sort of a Noah's Ark fashion to go to this Proxima b, which is the nearest exoplanet near Alpha Centauri. It's a rocky planet, maybe a lot of minerals here, but if you take the escape velocity from Earth, I think that's like 11 kilometers per second, and you divide by 4 light years, you get this fundamental timescale, which is 100,000 years. So this is 1/3 of the Homo sapien history. It's really very long. Now, a human would find it difficult even traveling to Mars because of radiation. We have computed that a travel to Mars, which takes about 2.5 to 3 years, would give the human about 1 sievert of radiation, and that is near the fatal limit. A few sievert will pretty sure give us cancer, and it's very impractical to have shielding of the galactic cosmic rays, which usually are GeV levels, and it's very difficult to come up with a superconducting magnet shield. We are shielded on Earth because we have a rotating iron core, which protects us from radiation damage. But carbohydrate life will have a very hard time leaving the low Earth orbit because we're leaving the magnetic field of Earth. However, all these AIs, all these neuromorphic things, and all the machines we built can survive this voyage. I did some calculation that the erosion of your spaceship, you just need like 10 centimeters, and you can survive the erosion of all the radiation. And 10,000 years is actually a magic time scale because we know nuclear energy is 1,000,000-fold more powerful than chemical energy. And so even with today's nuclear power, you actually have enough energy to sustain travel of these silicon-based life forms, if you call that, whatever you call that, to the next exoplanet. And in fact, you have enough energy to travel within 10 parsecs. There are actually 100 exoplanets within this distance. And in 100 rocky planets, for sure, you will find more uranium. And so you can actually populate the entire galaxy with AIs. So I actually made this cartoon, which is what you need really is recycling. You can be driven by nuclear energy, and then you have a closed ecosystem, and you need these AIs to, anneal materials. Unlike, humans, you can take a temperature, you can raise it to, 500 Celsius, you probably can anneal a lot of the damage. And if annealing doesn't work, you just melt it and recrystallize it. You can have a material cycle in here. And then you can have the AI doing materials experiments. Every material is a little cosmos. The microstructure evolution is very like biological evolution. There's a lot of things to be understood about materials when you do this kind of exploration. But this is not for humans. So I think I just end that I think we only have one system for carbon-based life forms, and we have to be very careful in things like climate change, nuclear war, and these two have things to do with nuclear, and crazy AIs. The crazy AIs, they can have the whole galaxy, but we only have this particular system. So I actually wrote a perspective recently, and you're welcome to read that. Thank you.
Sure, thank you for just a remarkable presentation. One of our members, Marv Goldschmidt, pointed out to us several months ago that when you look at practical applications of AI in the context that you described it today, we're really not talking about an industrial revolution, but more a cognitive revolution. And when you talked about and showed us in great detail and emphasis, self-driving labs, for example, their benefits and so on, it's very, very impressive. But I have to say, there was a moment when one of your students, Chu, was interacting with Chat in a CREST demonstration, and Chu said to CREST, or Chu said to Chat that he was heading for lunch. It reminded me that the Achilles heel of all of AI is energy, power. Whereas for human beings, I mean, we don't depend on the internet, or we don't depend on the grid. We depend on someone providing us with lunch for our energy. And I just wonder, in terms of seriously, in terms of a risk-benefit analysis, all of the emphasis, and you pointed out that AI cares about energy and money. And I think the energy commitment to AI is really humongous when you think about it. At least at the moment. And quantum computers could change all of that. Yeah.
Yes.
But the reality is there's a tremendous dependence. I don't know, we have an echo. I don't know. I'm not quite sure what. But
probably Jim, you're still sharing the sound.
Yeah.
oh, maybe that's it. Someone have a phone?
No, I think it's my sharing that's the problem.
Oh, I'm sorry.
Yeah,
Okay.
yeah.
Oh, no, I'm with you. So my question is the risk-benefit analysis something that we should be concerned about? I mean, the potential is enormous, no question. You've demonstrated that. But it comes at a cost, and the cost is going to be energy and money. And so we have somewhere along the lines, don't we have to think about that? Don't we have to put that into the mix? I'm just curious
Absolutely.
about your thinking.
And I think this is why the word agentic AI is necessary, because of distributed interest. I think politics is a key part of the conversation
Yeah.
because it controls who have the power, electric power, who has the money. And I think if not managed well, the rapid change in the economy could really fracture the body politic, and it could be very ugly. And I really do worry because it's a political conversation of what do you optimize for.
Yeah.
And already we see that Microsoft, Google, they are grabbing nuclear energy. They actually want to build data center right on the site of the nuclear power plant because that's the most assured base load. And that
Yeah.
is going to degrade the power quality of the,
Mm.
of residents, right? So of humans.
Yeah.
And so there is going to be a fight for electrical power in the next decade. And I think we really have to understand, this is, given the political situation, we have to understand and manage that.
Yeah. Yeah. Well, it gets it. I mean, the politics are really emphasized this week with the discussion between Anthropic and the Department of Department of War, I guess it is, or today. But anyway, their hands up. Let's move on to Albert. Your hand was up.
Yeah. So regarding that issue that you came up right now, with the energy going to be a determining factor, I wonder whether AI is being misused to answer silly questions because nobody's paying for the price of energy and all these complications. And then whether it makes sense to start to charge such that people don't use it willy-nilly and leave it for the real issues of science, the kind of stuff we've seen today. And the
Absolutely.
question is, who in society going to make this decision?
So I think most of AI has been used now to process our privacy. They really monitor us and learn about us. But it has run, I think, going to be run into a data crunch because there's still a lot that we don't know about the physical world, about science engineering. And in the future, AI may be driven towards doing more experiments, the type of kind that I outlined. And I think, spending electricity to do silly things like Bitcoin mining and these things are really not good. And again, it's a political question of, who is it for, this AI?
Yeah. Marv?
So, first of all, over the years that I've been involved in developing some of these technologies, this is the use we were hoping for. So I really appreciate getting a non-dystopian view of how AI can be used because that's not the common sense out there. I did note this is actually more of a transitional question for you. I noticed that some of the early work that you had was being used, like in late 2023, you were utilizing GPT-4. Now, obviously, this has gone through. When we say we're at GPT 5.3, literally that's orders of magnitude improvement. I'm wondering how that lack of stability. When do you incorporate a new AI? Because we're getting since November, we've had 5.1, 5.2, 5.3. We've had Claude go from 4 to 4.6. All of them with dramatically different capabilities, larger context windows, everything else. So I'm wondering how you manage that issue and what type of changes you've noticed as you've implemented new models.
Great question. Indeed, we saw actually even day-to-day variations. Sometimes, the OpenAI have, less compute and it just answers stupidly in the 2023 days. And one thing we have done is, but a key point is actually privacy. Because as I say, all these new data there's value to them and it's political. I don't want to send all the data to open or whatever these big companies. So we are training at MIT on-premise models. We are able to train up to 200 billion parameter models on top of these open source neural networks. And that, of course, give us stability. So I think this is going to be a major thing because I think just sending all these valuable information to big companies is probably not going to be the future because that data is kind of eventually, your worth in the society, in my view.
Yeah, that is the argument for open source, especially in research areas, because if you read the license agreements with OpenAI or Google or XAI or whatever, they reserve the right to train based on the information you've given. Now, can you hide some of that? Theoretically, yes. Practically, no. So that is a big question. So the move towards open source makes a lot of sense in that case.
Yeah, I think in the
Actually, what
future, every one of us would have a few models to do things for us.
Yeah.
But that's going to be kept very, very private and
Eddie.
Yes, I'm just sort of going to make a few observations. Back in the 90s, I did a study internally for a company I was working for to look at the rate of change of technology and innovation over the course of human history, a bit like what you did in a way. And I didn't believe my own numbers when I looked at the potential for the future. And what I see now is, well, just to give you a few little touches, I saw a couple of papers recently, one on aluminium as a catalyst, which would change a great deal of the cost, for example, of creating new molecules and so forth. And free electron parallel spin superconductors. So new discoveries all the time. And really what we're looking at is rapid advances in terms of convergence. AI could enormously accelerate it by looking at various technologies and combining them to give new results. I don't know if you've had a look at that, in which the AIs actually produce something new, like an iPhone out of the convergence of multiple different other technologies. So it could look for opportunities in that context, because that seems to be the way that you're going. In other words, it's an advance above where you are. The final thing I will make a comment on is the idea of AIs inhabiting the galaxy. And the problem is you're faced with is the Fermi paradox. So, so I don't know if any civilization has ever actually managed to do what you're thinking, because I think at the end of the road, unfortunately, there is a limit to how much integration can be done and how much complexity can provide. And I expect the rate of evolution of new technologies and innovations to begin to decline at some point. But maybe that's just me looking too far into the future.
that's a great point. I think, how big of a spaceship we can lift controls the ultimate, range of inventions it can go. So I have also thought about that, and it's not clear. Yeah. And on your point of AI for design, so I work mostly on materials, but then also there is mechanical engineering and electrical engineering. You can, even people who are using multi-agentic tools to try to design something as a nuclear power plant. I think it may sound pretty ridiculous today, but if you look at how much the capabilities have grown over the past 2 years, because 2 years ago, GPT still give me fake references. It literally give me, two references if I ask it, but then those have authors but untitled, but those are made up because it's a next of word model. But today, when you look at it, give you a chain of reasoning, and it actually give you click onto it, it actually give you a real PDF reference. So I really think, yeah, design for engineering design is another big area of activity.
Good. Drew, I want to thank you once again for joining us today. You've shown us how important things such as the self-driving lab can be not only in materials research, but obviously it extends to basically all of science, engineering, and medical research, and it's being used in those areas. And I appreciate your showing us how valuable it can be in terms of your own work. The one thing that I worry about in terms of AI in science and engineering and medicine, for example, beyond science, engineering, medicine, is the political influence. You know, we're heading towards a political season right now with caucuses and all the other things that are happening. It occurred to me that if you look at the number of engineers, for example, who are elected representatives or senators, you can count them both on about one hand or maybe two hands at most. And yet, they're going to have to make policy decisions unless the president decides to make them unilaterally, and hopefully that won't happen. But in principle, Congress has got to make decisions, public policy decisions about the application of AI in terms of our life and our livelihoods. And I just worry that we don't have the sort of understanding in our political infrastructure to be able to do that intelligently. And I think that's where we, scientists and technologists, have got to speak out. And I really appreciate what you're doing and what you're publishing because I think it does educate. And hopefully some people on the staff of congressmen and senators will be reading some of the things you're publishing. I appreciate that. And I don't want to, I know I sound very somber and I don't mean to be, but I think this is a very important issue. And you've given us a lot to think about today. I really do appreciate that. And thank you for joining us once again.
Thank you so much, Ron. It's a great pleasure.
All right.
Great to meet you
Folks,
all.
folks, we'll meet again in 2 weeks. Vince Dixon mentioned he's going to talk about things related to Evacuation Day and the goings on in Massachusetts heading up to our Declaration of Independence. It'll be a good conversation for us. Meanwhile, have a good time. And Joe, again, thank you so much for this wonderful presentation. Thank you.
Thank you, Jim.
Thank you so much.
Okay. Take care, guys. Bye-bye.